I'll be tortured.
Okay.
All right, so let's get started.
Okay, yeah. So I think today we can have a progress of our each project, and so maybe I can start. So I will introduce the node detection part, and so maybe I will just open my slides. So there was 1 minute. Let's see. Okay, so can you see the slide?
Yes.
Of you?
Yep.
Okay,
Yes.
so what I did today is I after so I will apply the node detections on both the X-ray and the CT scan because maybe in the future we may need the node detection on the CT scan to generate the true the true ground. So right now I will just show some results and I will just explain some methods. So this is the outline. I think everyone have saw this before. So this is node detections because that is a very important part for our project. And if you saw that many companies they have they will do the same thing. So I think that is some essential part we need to do because we need this part. Okay, so today I have 2 parts. So the first is the node detection in the X-ray images. And today I will just explain the method. And in here's the method called a faster RCNN. The reason I will use this is that it is a official method and it is used in some some big company, for example, Facebook. Facebook released this code, and it is papers. It is the best paper for some very big conference. So I think so. It showed that the the results good and the speed is good. So I think that we can just so I will try this method first. And later I will just briefly to explain what is this method. And this is the data I'm using. So this is the NIH data set. And it also has some position of the nodal. So that's the reason I will use this data set, and it can help me to train. And it can help me to train the model to recognize where's the nodal. Okay, so that's, and this is the paper. So this is the first RCN. So if you are interested, you can just Google this paper. So right now in this slide, and I want to show what I'm going to do right now. So if you get images, so for example, that is X-ray or others. So there's some 4 type of analyze. For example, for the first one, it is just images, and you can do the classification and to say this images is a cat or a dog, but that is not what we want to do. And the second one is that we want to locate where is the cat and also do the classifications. And this is much like what we would do. And because we need the position information, and we also need to know what is that. And for this object detection, so that is what we are going to do. So in here we have many, how to say this, yeah, so it can just recognize many objects. And so, yeah, so what we are going to do is the object detection, and it can recognize many objects here. And so in here's it, there's some typical methods we'll use. Many people they will do. So in here's the faster RCN is the method I am using. So is this good so far? Okay. So here's just a slide to explain briefly about the method. So for example, you have images, and this is the input. And what we need to do is to have some know the position of this, and this is the first step. And the second step is to know what is that inside this. So we have two steps. So the first step is to know is that the object inside this, and the second step is the complications to know is it is a nodal or not. So I think so that is what we will do. And here's a process of how to train this model. And for example, in here we have a classification loss, and because maybe that is a node or it is a fake node or others, so we have a loss function here. And we also have a boundary box because we have a box over here, and we need to know if that object inside here. So use loss functions. So, and this is the real, how to say, the structure of that model, but it is a little complex. So maybe if you are interested, I can explain this. But I think that is what you need to know about this method. So here's just some. I have used some data sets and to briefly to train this model, and then the model is not so perfect because I still need to decide how many layers or others. But here's some result about this. So for example, it can just can detect there's maybe a node over here, and for this one, and maybe it is a node here, and there's also some results after you input these images, and it can just detect some place, and of course this one, and there's other images, but the result is in some cases it is not so good, but so far we have the first result of these nodal detections. So anyway, so in summary is that I build a method, and I use the faster CNN, and I use this data set to train this model, and it can have some power to detect some nodes, but it's not so perfect, so it needs some time to improve this. So this is the first part.
I have a question.
Yep.
Yeah, I have a question. Is that a unsupervised training? Is that unsupervised learning? Is a classification the feature purely defined by the neural network itself, or is it supervised in some way?
No, it is supervised because we need a training data set. So we need to provide many training data set using NIH. So we need to.
What kind of marking are there in this data set?
You mean the data set? So in that data set, there's many images, the X-ray images, and it's also included the labels. So that is the XY, the position of that. Yeah. So
it already include a label like with this crisscross shape where it is.
Yeah. Okay. So that is the reason I will use this. So there's still others X-rays data sets, and so maybe in the future we will use that, and maybe I will also try we'll call the transfer learning. That means we will just use other others model. It has been trained by others to recognize other objects, but we can just use some part of that inside here. But anyway, it is the first stage, and I think we can just recognize some nodes. So for the X-ray. And the second.
If I didn't remember it wrong, sorry. If I didn't remember it wrong, that data set also has been used for a previous or two previous publication by Andrew Wu's group in Stanford. Is that correct?
Yeah, it's correct.
So I guess the main difference between your approach and their approach is the neural net. Is the neural net constructed by you somewhat modeled after theirs?
Yep.
Did you try to replicate what they found?
I didn't do that because I only just downloaded the data set, and the method they're using compared to this one is, I think, maybe it should be powerful if I use it right. So anyway, I found this, it is maybe the best maybe the object detections algorithm, but I think there's no one use this on the lung cancer before, but I think we can try that. So anyway, okay. So the progress right now. And the second part is that we also want to know that because we also want to know the nodal detection in the CT data. The reason we want to do that is that there's many data sets and they have a CT scan. They already have the labels. They have the position of those nodals. So it can provide some truth ground for this. So so I also built some part of the method to detect that. And because the data is different, and I choose this UNet and with ResNet, and then maybe I will just explain later. And we also have a 3D CNN. The reason we use this is that there's many other people, they want to analyze this kind of data set, and they will use this combination. So I just repeat this one. So there's many data sets, and I found that in some competition, because some competition will provide this data set. So they have the CT scan data, and they also have the positions. So there's, compared to X-ray, we have more data in this part. So so right now, this slide just showed that the data, how to just prepare the data, because we can start from this CT scans. And in the first one, we need to just cut into some 3D clock, because then compared to that CT scan data, this is too small. And if you use a CT data to train that model, it will not be helpful. So we need to cut this first. And then we need to do some imaging pre-process. For example, we need to just smooth that part, or to do some, so we need to do some imaging pre-process, and then we need to do some data augmentation. That means sometimes we need to rotate that, or to increase the size of that. So then our model will have the ability to recognize some other different size of the node. And then we will have a positive sample. And at the same time, so that data set provides a false positive sample. And we have this process, and we can get the negative sample. So right now we have positive sample and negative sample, and we will just input into this UNet. And here's just a slide. I think this is the last slide, just to explain what is the UNet model. And if you remember that we have papers about you can use some neural network to detect the skin cancers, and there's a paper about that. So they use this UNet to do that. So I just use the same way, and but for each part it is a CNN models, and I use the latest the structure called a ResNet. And it is just like that. For each part, there's many layers, and the ResNet means that we will just connect each part. So it is a new structure, but if you don't know, that would be fine. So this is the way I would just to approach the nodal detection on the CT scan. But right now, I still not finished the code, so I only can just explain the method. So I think, anyway, the summary is that for the X-ray, and we use the best object detection method, and for the CT data, so we use the methods that everyone are using. So I think we can get some good results. Yeah. Yeah. I think,
Question?
yeah. Sure.
So, what is the full name for RCNN?
You mean for you mean
RCNN?
okay.
I mean the full name. Do you know the full name? Like the CNN is a convolution neural network, right? So what is R?
Oh, it is
like
original.
Like regional. Okay, so it's
Yes.
regional convolution neural network. Okay. So my second question is, what is the main difference between 3D CNN and the 2D CNN? I mean, yeah, I mean, how do they transfer from 2D CNN to 3D CNN? What's the main difference?
I think your question is that why I need to apply the different methods on the 2D data and the 3D.
Oh no, I'm just interested because I learned the 2D CNN on the online class, right? So I was just wondering what's the difference between 3D CNN and the 2D CNN. So they just, because 2D CNN is working on the 2D image, right? So 3D CNN, the input is the 3D data. So they're using the same process as the 2D CNN, just change the dimension. I mean,
it's just change the dimensions. For example, for the normal CN, you will input 2D images. And but for the 3D CN, it is input the 3D images. And for each layers, it will have 4 dimensions because you have the 3D and you will also have a future. So you will have a 3D for each one. So yeah.
Okay, so to change your dimension. Okay, cool.
Yep. Yes.
Okay.
Okay. So I think
I have a quick question.
Yeah, sure.
Is it for these methods? Do you have to pre-train the networks at all?
Yeah.
Does that help?
Yeah. So most of the neural network you need to have a training data set. So you need.
I said a pre-training.
Pre-training?
Yeah.
So what do you mean by pre-training? I mean,
as in running it through, so for example, for the nodule detection, running the images through an autoencoder, and then just taking the encoder and kind of freezing those weights so that you have a pre-trained network that you can then train for classification.
Yes. So I think yes, you need to do that because so for example, for this slide, it just the process here is to show how I can just create a training data set, and so after I input this training data set, and it can help me to identify where that positions and also know what is that object. So so I'm not sure is that a pre-training, but we need that training process. So and in here's we have a UNet with ResNet, and in here's it can just recognize that object, and in here's we have a 3D CN. The purpose for that 3D CN is the classifications. So maybe you can say that this is a pre-training, but so anyway, this is a classification, and it can recognize where's that object.
Gotcha.
Yeah. So it's like a location. So UNet, ResNet can find a location, and 3D CNN do a classification. Is that what you mean?
Yeah, you can say that.
Cool. Okay.
Yeah.
Okay.
And I think those are the latest the methods, and so if you're interested, I can just provide some papers, or we can just discuss later. But I think we will see because there's still some part I need to improve that, and so I'll just continue to improve this part.
How are you?
Yep.
Sorry, go ahead.
Yeah, so I think right now just what I did is to just in focus on these two parts and do the nodal detection on the CN and also X-ray and to improve the ability to detect the nodules. I think that is the thing I would do right now. Okay. Yeah. So
what's the nut was about to say?
Oh no, I'm just where are you training these models?
I have I use my my laptop.
Really?
Okay. So how long did you?
I have a laptop, but I also have a desktop and I have a GPU. So yeah.
Okay.
So I will just.
So how long? I mean, did it take a few hours or just 10 seconds? 10 minutes?
Few hours.
Few hours. Okay. Few hours. Okay. That's quick.
Yep. It is quick.
Wow.
Okay.
Okay.
So I think I think this part. So.
So I want to ask a question. It was very nice to see that you are able to get sort of nodule candidates from X-ray, and also a layout of how you are going to approach the three-dimensional nodule detection task. How would you want to combine those two? Do you want to then, because in the end the goal is to have 3D data as ground truth, generate X-rays so that we can train nodule detection based on those ground truth marked X-rays. Do you then later on want to use the ground truth marked X-ray to improve your 2D nodule detection algorithm, or do you want to just use that as a data set and rely on the learning capacity of that algorithm just to learn to the extent what it can? Do you have any interaction between the algorithms on the algorithmic level, rather than having one algorithm feeding the other just the data set? Do you have any algorithmic level dialogues?
I must say that to the purpose to build those two methods may not right now it is focused on node, but maybe in the future maybe we need to do other parts. So I will just build those two. And next step, after we have a good 3D object detections, maybe we will use the data set, and maybe we will use Sonnet method, and it can just transform the 3D model, 3D CT data to the X-ray, and that means we may have the position of that node, and it can help me to improve the abilities for node detection on the X-ray. So next step, it can help me to improve the 2D nodal detections, and in the future, that algorithm may help us to do other jobs.
What other jobs? I would like to know.
Yeah, so because right now we need to do the nodal detections, but because our final goal is the 3D reconstructions, right? So maybe we need to recognize other parts. Yeah, so because...
Oh, okay. So you say your 2D nodule detection algorithm with some tweaks might be able to turn into like a ribcage detection algorithm or a heart detection algorithm, sort of.
Yeah, because after we have that algorithm and we use if we have some data set about maybe the heart, and we can use that. And of course we need to train again, but we can use the same method, same code, and to recognize the heart. Yeah, so
given you have the shape of the heart marked on the X-ray, generated from CT scan, and the heart generated from CT scan was marked by your UNet plus ResNet and 3D CNN kind of thing in another tweaked format. Is that correct?
Yeah, you can say that.
Okay, okay. Oh, that would be very cool. It's kind of like generating a pair of CNN and have them morph into different, have them morph accordingly, one in 2-dimensional, one in 3-dimensional, and have they morph to the places they want to they want to recognize.
Yeah. So for
Okay.
example, maybe we need to, for example, for the 3D reconstruction, maybe we need to identify where's the points. So right now, so maybe we will use the segmentation right now, because segmentation can mark those regions, but the object detection is another approach. So I mean, after this code, I think we have tools we can do every kind of object detections. So you can do the node or heart or the bones. It depends on your training data set.
Very cool. Very cool.
Okay, so who want to present next? Okay, so you want to share the slide?
Yeah, sure. Let me open the computer. Do you see the slide?
Yeah, sure.
Yeah, okay. So I'm working on the 3D reconstruction and focus on the lungs and the rib cage. And in fact, I spent some time to run through the tutorial for OpenGL. So this is just some preliminary results. But so for today, I didn't show result on OpenGL. Okay. So basically, I follow this paper. This is in the 2011. So basically, they built a simple lung field model and the rib cage model using the just the outside of from your 2D image segmentation. Okay, so I assume that we will have a 2D segmentation, and my final goal is to build the 3D computer graphic model of the lung and the rib cage. Okay, so this just some so basically what I do is that I draw a circle. So I assume what I will have, so maybe from, I don't know, I will get the lung segmentation, something like that. That's my assumption. So first I did the any edge detection, very simple. So I got the edge of the lung. Then I use this is like preliminary trial. So I use a very common used library, the Tzu-Ching, which can help me to do a Delaunay tetradehydration. And so this is showing the 3D point. In fact, this is a 3D point, and this software can help me to do this, to make the 3D point cloud become like the mesh. Okay. So, but the problem is that this software, the license is free for academic, but not for commercial. So I guess finally maybe we cannot use it, maybe. So, but however, it's just a first trial to see how to do a 3D reconstruction. But in the future, I guess I will use the OpenGL. Okay. And then for a rib cage, I think I will follow the paper in 2009 from IEEE. So they use a health torus, which is just like a tube. They basically try to use a very simple model, like a tube, like a bending tube, and you just from the 2D image. So this is on the left top. This is just a frontal image of a 2D image. If we can do some simple image processing, we can segment out the region of the rib cage, and just we can build the simple health tube model like the left bottom image. And so this is what I think I can do. I will follow this paper. This will be the first simple 3D reconstruction of a rib cage. Okay. So again, what I do is that I just assume what I will get is like a simple segmentation result of a rib cage. So somebody will give me that. And there's several image processing steps. So first I do a distance transformation. So I can for each pixel I can get the the distance from the center to the edge, so I can know the radius of the rib cage. And I do a surveil filter, and I use the zero crossing sealing, so I can get the center of the rib cage. So and in this case, right now I get all the information. I think I get all the information I need to rebuild, because once I get to the center and I understand for each center point I got the radius of the rib cage, I think from this model, if we can get a clear segmentation like this image, then I think it's very easy to build the 3D model. Okay, so this just, sorry, so today just showing some preliminary results. So most of the time I study the OpenGL, but I think right now I have set up the OpenGL and OpenCV on Visual Studio and ready. So I think in the future there will be faster result. There will be faster result showing there. Okay.
Yeah. So I think I will just have to explain that, because the Ray and the Kate, they will just provide the 2D segmentation results, and for example for this lump, and just the weight height will just continue for that, from that 2D segmentation results for the bone and also for the lung field. So it depends on the 2D segmentation results. Yeah. So yeah. Yeah. So I think it is the first step that we can just build a 3D model to do the 3D reconstructions.
I have a question. So, Wei-Tai, where did you plan to get the 3D ground truth for these segments? Like for rib cage, you need someone to tell you where. You need someone to tell you what rib cage really is looking like in that given X-ray, and most of the time it's how did you determine whether you're doing a blind guess, or are you really referring to a ground truth that is the real shape of the rib cage that you're looking at?
So let me share the other slide. Okay.
Okay.
Let me just close this one, and how do I do it?
Yeah, you have a supplementary data.
No, so it's not data. Just I want to show like the other paper. So to answer your question, so I think that's it's not the like in the future step. Let me so how to do that? So I will.
Maybe you can close the sharing and start again.
Okay. So I will just start sharing and share again. Which one? This one. Okay. Can you see the screen?
Yes, I can.
Yeah. So I think for right now, because it has been a long time for me to do the computer graphic, so I need to spend some time to see how to do that. So my first step is how to draw those things. So that's my objective right now, to how to draw those things. And to answer your question, I think this might be in the future. I mean, this will be in the future. This might be the structure to say how do we know how to build the model of a rib cage. I think I will follow the step like from this paper. So basically, use the SSM model, and we need some training data to build this SSM model. So in this case, we can get the rib cage. The rib cage model, yeah, and there's some training. Basically, after building this model, we can always compare the future image with this model and slice into 2D using the 2D image comparison. Yeah. So is that your question? I mean.
Yes. Sorry. You should go first.
No. So I'm good. So any questions?
Yeah, no. I mean, George, do you have anything to say?
I think that so what I want to ask is that maybe you should just the ground truth data, maybe the CT scan data. So maybe we need to from the CT scan data, we can have a 3D shape of that, and then we can input to that static shape model and to have that static models. So I think that is what we want to know, right?
Yeah, that's
So
the
the ground
concept.
truth is the CT data.
Yes.
And even this is CT data. CT data is a multi-voxel. It's a bunch of voxels.
Yes.
Oh,
Right. It's a bunch of voxels. So there is inevitably going to be a segmentation on a three-dimensional level.
Mm-hmm.
Is that later on going to be instructed by what George has been working on?
I would. In my original plan, that might be the what Ray and Kate they would do, because I would expect they would do the segmentation, but it depends. So if there 2D segmentations, the progress not so fast, so maybe I would try to do that the 3D segmentations for the CT scan. Yeah, so it depends.
Okay.
Cool.
Traditionally, though, I am not very familiar with 3D segmentation. Do you think, I can ask around if you don't know the answer, but do you think 3D segmentation is hard for chest CT? Do you think getting the heart and or the rib cage and or other like bronchi and vessels from the chest CT, is it a hard job traditionally for them?
I think if you only want to get maybe few samples, for example, maybe the 5 of 10, you can do it one by one. So it is not hard, because you can just maybe decide a threshold and you will get some segmentation results. So it is not hard. So I think the problem is that if that is a general models, if you want to input any data to this and get 3D segmentation, that is hard. But for the weight case, I think he only needs some input data from the CT scan. So for example, maybe just 10 shapes, 3D shape, and then he can get some static shape model. So I think that is not hard.
Okay.
So, but if you prefer,
yes.
Yep.
Okay.
So yeah. So want to present next, or
Sanad.
I have slides for you.
Cool.
But I can give you an update as to my progress on the CT pipeline. So CT to X-ray generation pipeline. So the one that I had shown you several weeks back was not up to snuff, basically, according to what we needed. And so there were several problems with it, including the fact that the X-ray images, first of all, it was slow. The X-ray images weren't coming out as good quality as we expected them to. And they were kind of warped, which isn't really a big deal. The main problem was the quality. And so what I've been doing is kind of rewriting the pipeline from ground up. The previous approach was kind of heavily relying on a lot of Python to help, just because it's easy and fun. But now I've kind of been writing most of it Python, using Python as just kind of a skeleton, so we can interact with it easier and integrate it more easily into an application that we'll eventually roll this into. So I've been writing the main stuff all in C, and learning about kind of taking advantage of parallelization and kind of image processing in parallel. So I've been learning that, working with kind of trying to take advantage of all the computational resources we have, so that we can roll this into a modular application. So something that not only can just spit out X-ray images given specific angles, but if we ever needed to do something more, or if we ever need to add functionality in the future, it'll be easier to add that functionality to this. So it's not like a one rigid code. I'm trying to make it so that it's more modular and workable. So a lot of it has been bogged down in kind of the specifics of kind of making it memory optimized and able to take advantage of the parallel I can't say that word, parallel processors that are available to everyone.
Cool. So I have a question. So when you use Python, there's many library you can use for the image process, file fees. You maybe some function you need to write by yourself. So
yeah. The reason I'm straying away from Python is because I want to. It's just a lot easier to optimize in C.
Yep.
Python makes it really, really easy to say something like to perform transformations and different things on images and stuff, but there is a lot of more related, like low-level memory-related optimizations that you have a lot more control over in C. And there are Python libraries that in the back use C in their implementations to kind of speed things along, but I've just found that it's just easier to skip that and just directly hash out everything, especially because it makes it easier to, again, integrate with a future application.
Cool. So I think your part is important, and I think the most important is that if you can get a high quality of the synthetics.
That's what I'm looking for, yeah.
Yeah. So we expect that your result.
Yeah, I'm sure I'll keep everyone posted, because basically for the next, let me see, 2 weeks, we have a kind of break between classes here at Hopkins, so I'll be on this full time basically over the next 2 weeks. So I don't have any other obligations except feeding myself. So yeah, and
so I have a question.
Yes, sir.
Oh, sorry.
No. I was going to say, if you need support in any other capacity, I'll be doing this full time, but I'll also be free to help out in anything you need, even non-engineering related. So. Okay.
So one question I have is, as you mentioned, it's both a little warped and also a lower resolution than you might have expected.
Yes.
So have you found the root cause for those two? Like what caused it to warp?
What caused the warp was bad math.
Oh, okay.
So that was fixed. What caused the lower resolution was basically the let me see if I can find the exact. Basically, there's in order to kind of compute it down to a pixel, like a grid of from a 3D, from basically the main premise is that you take the 3D box, rotate it somehow, and then squash it into a grid. That's in a nutshell. And so in that squashing, basically, as well as the rotation, the rotation has a lot of rounding errors that Python introduces. And then the squashing also has a lot of errors because things don't line up evenly into grids. And so Python rounds this way and rounds that way and just squishes this and squishes that. And there's a lot more math that you can do to kind of specify and make sure that that doesn't happen. But then running something like that in Python is very, very slow. To do all the math we need, I don't want to write that in Python because it's just going to bog down my computer, the process. And so that's why I'm kind of rewriting that in C so we can get a more efficient, again, memory optimized implementation. So we don't have to cut corners yet. We can do all the steps that we need to do in an efficient fashion.
So several of the causes were either a math problem or a computer's intrinsic tendency to data loss.
Yeah.
So,
which I would have more control over writing it in C.
Okay. How do you feel about even if you improve on all of those and get rid of those as much as possible like you can? Do you think there are ways that you can somehow apply machine learning? I just want to throw this out kind of freely. So this is free thought. do you think there is any room for machine learning in your part that you can somehow compare what is the difference between your most optimized CT generated X-ray and the real X-ray that are existing in databases, like the database that George used to train his nodular detection algorithm? Do you think there's any like interaction and I will recognize that this is something I don't have experience in, and I don't have a lot of things to say because I don't know how to define ground truth, and a lot of things need to be maybe unsupervised learning. But yeah, not only for you, but for George and for Wei Tai, do you have any thought on? Yeah.
There's okay. I have an idea based on my limited machine learning coursework. George, please correct me if I'm wrong. Basically, an ML approach to figuring out the difference between these generated X-rays and real X-rays would be basically to build a conditional GAN. And so what I envision doing is you basically have a data set of real X-rays, and then you have a data set of my fake X-rays. And then you learn some low dimensional, you run the fake X-rays through what we call an autoencoder to get some low dimensional representation of them, basically. And then you use those as an input to what you call a generative adversarial network, which basically means I feed in this low dimensional representation. It tries to create an X-ray image based on that. And then that's the generator. Then there's the adversary or the discriminator, which takes this and tries its best to determine whether this X-ray image came from Sanat's data set or whether it came from the real data set. And so what happens is you train them in turn. So you train the discriminator so it gets so good that it knows that this is fake and this is real. And then you train the generator so that it knows that it gets better at generating the transforming my fake ones to look more like real ones. And so you keep doing that back and forth until the generator or discriminator can't tell anymore whether or not this came from my fake data set or whether it came from my real data set. And the reason where you would use my fake data set is, again, is the kind of seed to prompt the generator to create the kind of image you're looking for. And then the real data is used almost like to copy the style of the real data. If that makes, that's a very high level overview, but
yeah.
Isn't that the original thought that George wanted to use to generate X-rays or three-dimensional three-dimensional structure from that? Okay.
Yeah.
Is that GAN? Is that?
Yes.
Is that GAN? Yeah. It is.
It was.
Yeah.
I think I have a slide to explain that. Yeah, that is GAN. But for me, I think that is a one. I mean that for imaging process, sometimes we need to just generate something that images. So, for example, for the paper I'm writing right now, I also create something that images. But there's only in most of the cases, we will not try to distinguish from that to the real images. What we would do is to prove that it can apply to the images, and it can also apply to the real data, and it can show our evidence good. But there's only a few research about you can just compare with those two. So I think what we need to do is maybe we need to do a search about the papers if there's some papers to do that, and I think it can, can prove that our methods are good, and we can do that based on that papers. And there's also some ways we can just to compare with those two, but it case by case. There's no general ways to do that. So I think what I would do first is to find some papers, and if there's some process, and maybe we can do that. Yeah, but yeah. Yeah, so yeah.
I actually I like very much what Sanat and said about GAN, but one thing I want to ask is, so say you successfully apply GAN and you make a transformation step very well, so that you transform what you originally projected from CT scan into something that in its detail very much looks like a real X-ray. Do we have then measurable means to determine this step is necessary for a better performance of our nodule detection algorithm? Say, okay, so my thought is this: can we find a way to prove that with this transformation we can train the nodule detection algorithm better? Like using the raw CT projected X-ray as a data set, like it is. Say we say it's X-ray data set 1, and we use a transformer data set and say it's a data set 2, and we use that, both of them being marked where the nodules are and where other places are. Will we expect, is that a good framework that we can from that learn how much we improve by doing that transformation? Is that more of a presentation necessity, or is that something that you were convinced deep down in your mind? Because for presentation, we can, if there is really a difference, we can say, oh, we did this training and we did that training, and the two trainings with two different data set resulting drastically different outcome, and then we'll say, yes, this is very nice. But do you think, because they will have a problem in this step, because we'll have to duplicate our training resources that we put in, right? We have to train 2 nets with 2 sets, right? 2 sets of data. Do you think that this investment is going to be necessary, or without this kind of duplication of invested resources, how else way would you prove the other way? Like you don't need this duplication of resources invested.
I think the main purpose we need to think that or generate those X-ray images is that if we don't have enough training data sets, and we need to use that, because in most of the neural network we need a lot of the training data set, then we will have a good performance. So we need to think that they are the same data set. So yeah, so I think that is the main purpose. So that's the reason we need to prove that synthetic images is good enough, or just like the true images. So I think that is the main purpose. But I think that Sona just mentioned about again that process. So maybe that is a good idea. So we can maybe ways we can just to distinguish from the synthetic images or the real images. So I think we can think about that. I think that is a good idea.
So now what are you about to say?
Oh, I don't remember.
Uh-oh.
Oh, I was gonna say I don't think it's that much investment of resources that we should be concerned whether or not we should do both. Or not. I think your idea definitely makes sense, and I think that it's definitely worth trying out. It won't be too resource intensive.
Yeah. Okay, that'll be cool. Yeah. Alrighty. Okay, I think that this meeting is unexpectedly very fruitful. I think this is the most progress we've made in past year. I don't know, just yeah. Oh my, very good.
Cool.
So in the following few weeks, what are your future plans? In the following 2 weeks, to be honest, I will be very, very bugged up with my thesis meeting. I will be willing to attend the meetings and give my thoughts as I just did, as I've always been doing. But you know, first I cannot engineer is the problem, and and second, I think in the very short term we are not going to have a funding resource like this month. No, so this is something I cannot do from this short time frame. But yeah, there are the things.
I think for the next meeting, so I think maybe I could just meet one by one, and because it maybe have a high quality of the discussion, so maybe I will just meet with each of you, and not including the set, so you can prepare for your. Yeah, so I will meet with. Yeah, so okay. Anyway, I think you don't need to worry about this part. So I think. The progress of the weight he will need some time, and for me I will need some time. But I think I will catch up with there's progress. So don't worry about this part.
Okay.
Yep. So we will just wait for some good result.
Okay. And be reminded that Sanat is totally free these 2 weeks. We need to squeeze in the maximum way we can. All right. Thank you so much for your time.
Yep. So I think
any more like last questions and issues that you want to raise?
No.
Do you have any last? Okay.
At the end, I have a record this meeting, so I think I will just put on YouTube, so you can just watch that.
Okay, yeah. If you can send us a private link to it and set the video non-public.
Yeah, sure.
That would be great.
Yeah, I will put the Slack and please check the information on the Slack.
Okay.
Okay, so
all right.
Good luck for everyone. Thanks for everyone.
Thank you.
Yeah, it's good. We are all in the same time zone.
Yeah.
We have no time zone difference.
It's
11:05 p.m.
Yeah. Okay, so right. Thank you, everyone.
Good night, everyone.
Thank you so much for your time and effort. Have a good night.